Hi there, Science 10. So you are starting today your new unit on the topic of energy, but before we got that going, I thought I'd show you something. It's the new lab. So here we are in room 406. Not sure if any of you have worked in this room before, Ms. Steinke's room, but as you can see, huge changes here, and I, for one, think it is pretty awesome. So, wish you guys could be here to experience that. But anyone who's taking classes next year with Ms. Steinke is going to have a treat of working in this room, be some of the first students doing that. So, looking at energy as the topic of the unit, we're going to look at energy. We're going to look at energy in the environment, how it changes forms. We're going to be kind of working towards looking at ecosystems, how energy changes forms in ecosystems, and also looking at climate and climate change. So that's the direction of this. I hope by now you've maybe looked over the notes package that I posted a few days ago. If you haven't done that, please do that. And do watch those videos that go with it just while you're waiting for things to ramp up a little bit more here. So energy. What is energy? It's the ability to do work. And what is work? Well, work is a force that's applied over a distance. Now, when I say work, we're not talking about homework or anything like that. The physical definition of work is exactly that. A force is a push or a pull, and if you exert a push or a pull over a distance, then you're doing work. So I'll give you an example of something that does not work. So here I am, pushing on this lab bench right here. The lab bench is not going anywhere, and so as a result of that, I'm not said to be doing any work. In the same way, an object, say, hurtling through space, might be in motion, but it's not doing any work. It has energy, but you need to apply. Work is force over a distance, and energy is the ability to do work. So you need force and you need a distance for work to be done. There are different kinds of energy that I'd like you to consider. In the notes, I have you maybe expanding that a bit and giving some examples. If you couldn't think of any examples of your own, I've written up here some for you to put into your notes to kind of expand your understanding a little bit. Forms of energy we're looking at. One is thermal energy. And an example of that is of something that has thermal energy would be hot water. Thermal energy really is just the energy of particles in motion. So for there to be thermal energy, you have to have some sample of matter, and the particles have to be in motion, which they really always are, actually. So all matter always has some thermal energy in it that's the content of the motion of the particles inside it. And that thermal energy can do work on other objects. Let's look at an example right here to kind of make this a bit more concrete. So I'm going to start up the Bunsen burner. There we go. Going. Okay. That wasn't supposed to happen. All right. So an initial temperature for this water in here is 22 degrees Celsius. So we're starting at 22 Celsius, and I just lost most of the hair on my wrist right there. What we have here is a system for transforming energy from one form to another. But let me first get into some of the other forms of energy to clarify that. Radiation is not what you think it is. You may think radiation, oh, well, that's bad. If you are thinking that, you are more likely to be thinking of radioactivity. Radiation is the energy of electromagnetic waves. What's that? This is what we think of as light, but what you might not know is that there are different forms of radiation, and light is just one of them. Light is the visible form of radiation, but we can detect the other forms of radiation because they are also forms of energy, all on the electromagnetic spectrum. They only differ by what's called their wavelength. We have lower energy, long wavelength radio waves, and at the other extreme, we have X-rays and gamma rays that have a very short wavelength and have a lot of energy in them. But it's all electromagnetic energy, differing only by wavelength. Another form of energy that we're looking at right now is chemical energy, chemical potential energy. I talked to you a little bit about exothermic and endothermic reactions, and I said how energy is stored in chemical bonds, and that some chemical bonds can release that energy in chemical reactions. Like specifically, by what I mean by the chemical bond is I really do mean bonds between one individual atom and another. So for example, right here, the bonds, the shared electrons that exist between the atoms of carbon and hydrogen in the methane molecule are what are being broken here. We're creating carbon dioxide and water, and because this is an exothermic reaction, an energy-releasing reaction, we have a production of heat as a result of this as well. Thermal energy. Mechanical energy is another form. We think of mechanical energy as the energy of motion, like the energy of a car in motion. We're going to get more into motion in a moment. Gravitational energy is another kind of energy, but this energy is one you can't really see. There is an ability to do work, making it a form of energy, but gravitational potential energy is energy that hasn't been released. It's a kind of potential energy that exists but hasn't been released. It can be released, and it's the energy of objects that are above some kind of reference point. So, for example, I might have, well, what's the nearest thing to hand? It's this striker. When I'm holding this striker here, it's about a meter above the ground right now. The striker is an object that has mass, and the reference point for the striker is the ground. So relative to the ground, the striker has gravitational potential energy. And we can release that energy just by dropping it, and we have an energy transformation from the gravitational potential energy it had to the energy of movement. There's also nuclear energy. An example of that would be the fuel rods that are used in nuclear power plants. What the fuel rods do is they release energy from the breakdown of atomic nuclei, and that becomes heat energy, which is used to drive a turbine in a nuclear power plant. And lastly, we have sound energy. If you've ever seen very loud music, like heard very loud music being played, and sometimes you might, if you've ever seen, say, a cup of water, a still water, with loud music around, you might notice that you get little waves inside the water. All of these that you're seeing here are energy transformations. I'd also like you to notice that there's really two broader classifications of energy here. One is kinetic energy. Think of kinetic energy as the energy of movement. I don't only mean things like the striker that can move when you drop it. I also mean particles that are in motion, so small you can't see them, but still in motion. And also radiation is a form of kinetic energy. Potential energy is energy that can be released but hasn't. For example, again, chemical energy is a form of potential energy. Energy exists in the bonds that can be released in a chemical reaction, but it hasn't been, so it's chemical potential energy. Let's zero in here and look a little bit about what's happening with the burner. So here, coming through the tube, we've got natural gas, methane. That burns in the presence of oxygen that's already in there. That's a combustion reaction. The oxygen's already in the air. This is a combustion reaction, and it releases energy. That energy is released in the form of radiation. Two kinds. One is light, and the other is infrared radiation. That infrared radiation instantly is heating up the air. That heat to the air is then being transferred. This has now become thermal energy. And by conduction through this mesh right here, that thermal energy is transferred to the water. The water now has thermal energy, as you can see from the movement of the particles. Also notice, we don't just have thermal energy stored in the heat of the particles, but there is motion in here as well. This is kinetic energy. I put this rubber stopper in here to show that the thermal energy, the motion of the individual particles, and the bubbles can make an object move. Again, what we're seeing here is different forms of energy and a transformation of energy. Here, I outline it right here. For our energy transformation example, we're starting with natural gas, chemical potential energy. It's transformed to radiation. Some of that is released as light energy. Some of that radiation is infrared. That infrared radiation is released instantly as thermal radiation. Some of that is released as sound, as you could hear, but some of it's released as kinetic energy. And of course, that thermal energy is being transferred from the air to the water. Another thing to clarify for your notes is this: 3 kinds of systems. I want to be clear about this. Earlier I told you about open systems and closed systems. We actually have to be a bit more discerning right here. Open, closed, and isolated systems are the 3 kinds I'd like you to know about right now. And an open system, like this open Erlenmeyer flask, energy can be transferred between the environment and the system, and also matter can too. You can pour water into an Erlenmeyer or pour it out, and it can get hot or cold depending on its surroundings. In a closed system, energy can still pass back and forth. You can heat or cool an Erlenmeyer even though it is sealed with a rubber stopper. Energy can be transferred back and forth. Here I have a system that's closed but also isolated. It's isolated because I put it inside a box. Really, what I want to draw here is a box that's entirely sealed. I've only kind of given you a cross-section of it. The linings of the box are insulation. This is the attempt at having an energy isolation of that box from the rest of the universe, specifically of the Erlenmeyer flask in there with whatever thermal energy the particles might have. Now, what will make this topic more challenging possibly is that we do also have equations. Here I'm going to just show them to you like this, here, and you can pause it if you want. And then here, the formula for gravitational potential energy, and you might have to rewind to this, 13 minutes, and the formula for kinetic potential energy, or kinetic energy, excuse me. So those are 2 forms that you can actually calculate using a formula. So how does that work? Well, first of all, you may be a little bit new to formulas, so I'll want to walk you through this a little bit. A formula is a mathematical tool we use to find something out. So for a formula, we're told these are different variables that are in the formula that we're interested in. And that if you know the value of some other variables, you can find out the value for one that's not known. In the formula for kinetic energy, we have 3 variables. One is kinetic energy itself, and that's measured in a unit called the joule, Joule. The other is mass. Mass is measured in an SI unit, the kilogram, and the last is the speed of an object. Speed is actually shown as v, for reasons that you'll understand better when you take physics. Some of you will, I think. The formula is kinetic energy equals 1/2 mv squared. Now, you might have noticed on the formula that it wasn't just big E, it was big E with a little k. The k tells you a bit more about the variable. The k tells you we're dealing not just with energy, but with kinetic energy. Ek is kinetic energy equals 1/2 of the mass times the square of the speed. That's the mathematical formula for kinetic energy. So if I give you an object's mass and its speed, you can calculate its kinetic energy, the energy of movement that it has. There is a formula also for gravitational potential energy, which you can calculate if you have other information. That formula, as you saw, EP, potential energy, specifically here we're talking about gravitational potential energy, equals mg delta H. There's probably a whole bunch you haven't heard in there. I will tell you this. Mass is always measured in kilograms. Mg delta H means mass times g times delta H. What is g and what is delta H? G is the acceleration due to gravity. If I take this striker right here and I drop it, it's easy to catch it after it's been falling for a fraction of a second. But a little bit harder for me to drop it and then try to grab it, oh I did, when it's almost hit the ground. Because as it falls, it gets faster and faster. Something that gets faster and faster over time, or slower and slower over time, it's said to be accelerating. Slower and slower, some people say decelerating, but that's a topic to talk about with Mr. Audette. Objects under the influence of the force of gravity, if they don't have other forces acting on them, they will accelerate downwards towards the center of whatever it is they're attracted towards. In this case, the striker is attracted towards the center of the Earth. If I drop the striker, with every second of fall, it will be going 9.8 meters per second faster. So a physicist would say 9.8 meters per second. So that's where the 9.8 meters per second squared comes from. It's a rate of change in how fast the object is going towards the center of the Earth. If you're on, say, Jupiter, it's towards the center of Jupiter. With gravity, it's all about a force that exists between two objects that have mass. More about gravity in Physics 11, but do be aware of that. Now, in the problem set I sent you, sometimes you are given a weight. It says the object's weight is such and such. And it'll give it to you and it'll say capital N. That might sound more difficult, but it actually makes the problem easier for you. Because in that case, your the weight part of that is mg. So I told you EP equals mg delta H. Mass times g is called the weight. It's the strength with which an object is attracted towards, in this case, the Earth. How hard a pull downwards on an object the Earth has. The heavier the object is, or the more massive the object is, the more its weight is. The distinction to make here is that mass is just the amount of material in an object, which is different from the weight of the object, which is the units of that are force towards the center of something else under the force of gravity. An object in, say, outer space, or let's say on the surface of a tiny asteroid, would have the same mass as here, right? If you take a 1 kilogram object on Earth, it's still going to be a 1 kilogram object on the surface of an asteroid. But on the surface of an asteroid, the weight is much smaller. If you're on the surface of a small asteroid, you can probably jump right off and go off into space. Your weight hasn't changed. Your mass hasn't changed, but your weight has. Because on asteroids, the acceleration due to gravity is less. So if you were given the weight and it says in N, in newtons, then they've already given you the m times g part of it. So that actually makes the problems a bit easier, even though you might not until now have heard of the difference between weight and mass. mg, mass times acceleration due to gravity, is weight. Now, what else did I want to talk about there? Oh, yes, of course. Sorry. The delta H part. The delta H, well, it's difference in height. Again, you may not yet have heard of, you can probably understand H because you've seen formulas like the finding the volume of a prism, length times width times height, right? So you know H for height. But what about the delta part? The delta part means difference, because for gravitational potential energy, we're always talking about a reference point. We can say, let's see, this striker right here has a different gravitational potential energy if my reference point is my hand. It doesn't have very much because it doesn't have far to fall. If my reference point is the ground, though, it has a greater gravitational potential energy. With gravitational potential energy, it's always about what energy does the object have relative to some other point that it can fall to. The longer it can fall, the greater distance it can fall, the greater energy it has for that reference point. So that's the delta H part. The delta means difference. The H means height. So delta H means difference in height. Now, what I'd like to do now, given that I'm putting up a worksheet on this topic, there's no worksheet for lesson 1, but there is one for lesson 2, and I'm assigning it today, is to go through some of the problems. One thing I've already told you is the law of conservation of energy. I told you that energy cannot be created or destroyed, although it can change forms like you just saw with the Bunsen burner. I've defined for you potential energy and kinetic energy, specifically the kinetic energy for a moving object and potential energy as gravitational potential energy. There's something else I'd like to show you, and that's this. We have this formula right here, EK equals 1/2 mv squared. I'd like you to note that you can rearrange that formula. You can solve that formula to calculate mass and to calculate speed. Because let's say, for example, I tell you the kinetic energy an object has, and I give you its speed, but I don't tell you its mass. With a rearranged formula, you can calculate its mass. Similarly, if I give you the mass and the energy, but I don't tell you how fast it's going, you can rearrange the formula to calculate that. In the rearranged formula for kinetic energy, mass equals 2 times the kinetic energy divided by the square of the velocity. Velocity is the square root of 2 times the kinetic energy divided by the mass. To solve problems like this, you need a calculator with the square root function. It's a bit easier to deal with gravitational potential energy. A physicist would say it's a linear system. There's no squares here, there's no square roots. You're just multiplying 3 things by each other. In this case, if we know an object's gravitational potential energy here, we can say its mass is potential energy divided by G times G delta H. In other words, potential energy divided by the acceleration due to gravity times the height difference. On Earth, that G value, and you need to know this, is 9.8 meters per second squared. That's something that if you take physics courses, you're going to want to know that. And delta H is gravitational potential energy divided by mg. And remember, mg can be, you can get that 2 ways. One, you can get it by someone telling you, here's the mass, and here's g. Or if someone tells you the weight of the object, then they've just told you mg. Weight is mg. There's 4 problems I'd like to review. Although I thought I'd like to show you something as well, because I want to get into energy conservation, make a connection here. This right here is called Newton's cradle. It's another example of where we can see energy transformation. In Newton's cradle, we have these steel balls, and you can lift one steel ball here like this and let it go. And what happens is the energy is transferred through the balls in the middle, and it magically, to some people, comes out the other side and causes the ball on the other side to jump up. And then that process repeats itself. Here we have an energy transformation. By pulling this steel ball backwards, I have given it gravitational potential energy, which would be measured by the difference in height between here, how high is it above the table here, versus how high above the table right here. That height difference, which is here about, I don't know, around that much, about that much of a difference in height, is going to be multiplied by m, will be the gravitational potential energy it has at that point. By the time it's just about to hit these other balls here, it doesn't have gravitational potential energy left, but it's moving. It's moving very fast. So that gravitational potential energy has been transformed. This is an energy transformation, and that then is transferred through the balls in the middle to the ball on the other side. So we have this system we've created here of energy transfer. Starting with gravitational potential energy, it swings. It has kinetic energy. That it gives that kinetic energy to these balls right here. The balls in the middle don't do very much, but they transfer that to this one here. So that's called Newton's cradle. Most of you will probably have heard of Isaac Newton by now as one of the greatest physicists who ever lived. There's some problems I'd like to review from your worksheet to help you out with doing this. But I do want you to think about this always, that here we have a system for transforming energy where gravitational potential energy is transformed to kinetic energy. And then back, by the way, because the object here that got lifted up, eventually it gets to this high point right here, and for a fraction of a second, well, instantaneously really, it's stopped. So as it swings upwards, it's slowing down and stops up here. And now what was the kinetic energy it was given has been transformed to gravitational potential energy. So if you know, if all of one has been transformed into another, then you'll know how much of that other form of energy you started with. Now, I wasn't very clear when I said that, but I'd like to review some problems that maybe will help a little bit with that concept. For the first two problems, you're just being asked to use the formulas straight up, not modify it at all. Question 1, I'm going to break down what the solution looks like. Here's the answer for question 1. When I am solving problems like this, I start by saying, what is my formula? Well, it's EK equals 1/2 mv squared because I want kinetic energy. What do I know? I know that mass for that problem is 2.1 kilogram and speed is 30 meters per second. Then I take those terms that I was given and I put them into the original equation. So we get EK equals 1/2 of 2.1 kilograms times 30 meters per second. Notice that I put 30 meters per second inside brackets because I'm squaring that speed. And when I do that calculation, what I finally get, my calculator tells me 945. What are we counting? We're counting joules. This is a unit of energy. So I'm going to want to have a J at the end. You've probably noticed that I actually wrote down 950 joules. I do that because I'm rounding off to take care of significant figures. If you were to answer this worksheet and give me 945, I'd be okay with that. But Going forward, you will need to learn significant figures to round off appropriately. We only know with certainty 2 figures, so I've rounded off to the nearest 10 right here. For question 2, I did the same thing. I said, hey, what do I want to know? I want to know gravitational potential energy. And I have the information I need to answer that. I start then with my formula, EP equals mg delta H. I know that the weight is measured in newtons, it's 12 newtons. So mg, the mg part, is 12 newtons. And the delta H, that height difference, is 21 meters. This is a straight multiplication problem. Gravitational potential energy equals 12 newtons times 21 meters. And I get 250 joules. Again, your calculator will tell you, oh, it's 252, but rounded to the nearest 10 with 2 significant figures, 250 is the best answer. For questions 6 and 7, what we're being asked to do is to calculate something else. You're given energy, but you need to figure out something else within that system of variables. So here, we're dealing with gravitational potential energy. We're being asked to calculate mass, the mass of an object in this situation. So you might notice on the worksheet that I made for you, I wrote down a formula that is rearranged. I want to make this easier for you. The formula you are using for this problem is m equals EP over g delta H. Well, what does that mean? That means that mass equals gravitational potential energy divided by g times the height difference. So, again, we're saying, hey, what formula do I want? I want this one. What do I know? I know that the gravitational potential energy is 6 joules. I know that, well, we assume we're on Earth, where g equals 9.8 meters per second squared, and the height difference is 3 meters. So I just take what I know, and I put it into the formula. The formula is like a little machine that does stuff for you. It does a calculation for you. Mass is 6 joules divided by 9.8 meters per second squared times 3 meters. That whole thing I just told you, the 9.8 times 3, goes at the bottom of the fraction. And I get 0.20. What are my units? Kilograms. So the mass is 0.20 kilograms. I again rounded that off to 2 significant digits. And the last problem is here, we're being asked to calculate the mass of an object that has kinetic energy. We use the formula mass equals 2 times kinetic energy divided by the square of the speed. Do we have enough information? Yes, because we're given the kinetic energy and we're given the speed. Then I take what I know and I put it into the formula. Notice that I put my answers inside a box. This is just good practice. It helps your instructors because they'll be like, oh, where is their answer? Oh yeah, there it is inside the box. Here, the box says mass equals 2 times 33,750 joules divided by 30 meters per second, and that's a squared part. I want to be clear here that g is 9.8 meters per second, 9.8 meters per second squared, which is different from saying a speed squared, where there it's like 30 meters per second, and that is all squared. I showed that here using brackets around that speed. And the value we get then is 75. The mass of the object is 75 kilograms. There are some problems that are a bit later in the worksheet that are maybe a little more difficult. They're a bit more difficult, but if you recognize that the law of conservation of energy is in play here, that gravitational potential energy can be converted to kinetic energy, then you can kind of back calculate a little bit. The last 2 problems on the worksheet call on you to do that. But I'm not going to run through them because I'd like to see how you do at them. I'm happy to answer those questions as well going forward. That's what you need to know for the first worksheet for lesson 2. I hope that goes okay for you, and as some of you will know already, we're getting to a point where we're starting to be maybe a bit more, getting a bit more active here at the school, so there will probably be a bit more greater volume of work happening, but I'm always also going to try and keep it manageable. I hope this helps, and I'll talk to you soon.